Hello everyone, we're going to talk about section 2.3, which is about linear models. So in section 2.2 we learned about linear equations, so now we're going to learn how to use these equations to model real-life applications. So the equations that we developed in section 2.2, these are going to help us create our linear models now, because those were just the equations, and so now we have real-life applications that we can apply the equations to create different types of graphs. So linear models are extremely useful in practical applications since they allow people to make maybe future estimates based on past and current data. It also gives us that big picture idea when we graph things to see maybe things are increasing or decreasing or staying the same, things along those lines. And the simplest way to construct a linear model is to use the line determined by two data points. So this means that if we develop an equation, then we can use two data points to really get an idea of our linear model. So we're going to dive into what that really means with our first example. And this is going to be number 1 and 4 in your book. And when I say number 1 and 4, I mean in the back section with all of the questions. Those will be number 1 and number 4. And I combined them to create our first example. So below we have a table representing the range of degrees of Fahrenheit and the range of degrees of Celsius. So we have Fahrenheit on the top there, and then we have Celsius on the bottom. For part A, we want to choose any two data points to construct a linear equation that models the data with x equals Fahrenheit and y equals Celsius. All right, so we only have to choose two data points. So we can choose any data points we want, but what I'm going to do is that I'm going to pick the very first data point, and then I'm going to pick the very last data point, just so we kind of get an idea with all the different data points in between. So if we do this, we know that x will be Fahrenheit and y will be Celsius. We can create our first and second point. So our first point, or x1, y1, is going to be 0. I always want to make x the top row, but it's reversed. So it will be 32, 0. And our second point, x2, y2, is going to be 212 and 100. All right, so we've identified our first and our second points. And since we want to create our linear equation, the first thing that we can do, we have 2 points, is we want to find our slope. So if we remember, our slope is the change in y divided by the change in x, which can also be represented as y2 minus y1 divided by x2 minus x1. So y2 is going to be 100, y1 is going to be 0, so we have 100 minus 0, divided by x2, which is 212, minus x1, which is 32. So now I want to simplify this. So 100 minus 0 is obviously just 100. And 212 minus 32, if you want to take a moment maybe to calculate this on your own, it's going to be 180. So we have 100 divided by 180. We can most definitely simplify this. So maybe we'll simplify it and divide by 10 from the top and the bottom, so we can simplify to get 10 over 18. And we can definitely simplify this further. So this time we'll divide by 2, and we'll get 5 over 9, and that's going to be its most simplest form. So now I have that our slope is 5 divided by 9. So now we can set up our linear equation. We do not have a y-intercept, but we do have our point, so we can use our point slope form. So we can use that very first point, that x1, y1. So we have y minus, move this up, y minus y1 equal to our slope, which is 5/9 times x minus x1. So this is going to turn into y minus y1, which will be 0, is equal to 5 over 9 times x minus x1, which is 32. And y minus 0 is just going to be y, so our final answer will be y is equal to 5/9 times x minus 32. All right, so we found our equation now. And for part B, we want to use this model to find the degrees in Celsius temperature that corresponds to 50 degrees Fahrenheit and 75 degrees Fahrenheit. So let's start with 50 degrees Fahrenheit. So we're going to write 50 degrees Fahrenheit. And since x is corresponding to Fahrenheit, all we need to do is plug in 50 for x and see what we get for y. So we're going to get y is equal to 5 divided by 9 times 50 minus 32. So 50 minus 32 is going to be 18. Then we can multiply 18 by 5 to get 90. So we have 90 divided by 9, which is going to be 10. And since this is y, we have 10 degrees Celsius. All right, so we found this is 10 degrees Celsius. Now we can use our initial chart to just make sure that this is correct. So if we go to our chart here, we know it was 50 degrees Fahrenheit. We obviously don't have 50 degrees Fahrenheit on our chart, but we know that 50 degrees Fahrenheit is between 32 and 68 degrees. So we can assume that this 10 degrees Celsius, which is also between 0 and 20, is correct. All right, so now I want to do the same thing for 75. Oof. 75 degrees Celsius. Fahrenheit, oops. Don't want to mess that up. So we can do the same thing as we did before. We have y is equal to 5/9 times, now it's going to be 75 minus 32. So if we subtract 32 from 75, we're going to get 43. Then we can multiply 43 by 5, and we end up getting 300, nope, not 300. Should be 215, there we go, divided by 9, which is going to give us something along the lines of 23.88. And so we get that this is about 23.9 degrees Celsius. All right, so we have 23.9 degrees Celsius, and our original temperature in Fahrenheit was 75. So 75 is going to land in between 68 and 104 degrees Fahrenheit. And it looks like 23.9 degrees Celsius also falls between that range. So we can assume that that would also be correct. All right, now for part C, we want to find when they're numerically equal. So we're going to do a little trick. since they're supposed to be equal, if they're equal, then there's really no point in differentiating between x and y if they're the exact same value in this certain case. So what we're going to do is that we're just going to set x equal to y. So if we just set x equal to y, then we can rewrite our equation, which was y is equal to 5 over 9 times x minus 32. And this is just going to turn into y is equal to 5/9 times y minus 32. And now I want to simplify down to our initial y and then solve. So we can distribute our 5/9, so we can get y is equal to 5/9 times y minus 32 times 5 over 9, which is going to give us 160 divided by 9. We're going to just keep it in fractions for our simplification. And now we want to subtract 5/9 y from both sides. That y is not in the denominator. And so our y is technically 9 over 9, since it's just one y. So if we subtract 5/9, we're going to get 4/9 y is equal to negative 160 over 9. And since both sides we see are being divided by 9, we wanted to keep that in fraction form because now we can just multiply each side by 9 to cancel out those 9s. So we can multiply by 9. Those all cancel. Now we have 4y is equal to negative 160. And I'm going to continue our work up here. Now we just want to divide by 4. And we get y is equal to negative 40. And this would be in degrees Celsius. All right, so now we have a value. And we really want to check. We want to make sure that this is correct. So we have that y is equal to negative 40 degrees Celsius. And we want to see if it's the same thing for x. So we're going to reverse it. We're going to set we're going to set our y equal to x, which will give us the exact same thing. So what we're going to do is we're going to set y equal to negative 40, and then we'll solve for x. That's how we're going to check. So if we do that, then we have our original equation, and here we're checking. So we have our original equation. Our y, we're now using negative 40 instead. And we have 5/9 x minus 32. And what we're going to do, because we really want to get rid of that 5/9, we don't really want to be dealing with fractions at this point. So we're going to multiply each side by 9 in order to get rid of that fraction. Oh wait, that one doesn't go away. Oops, there we go. Those ones go away. So now when we multiply by 9, we're going to get negative 360 is equal to 5 times x minus 32. So now we can divide each side by 5, and this should give us minus 32. That should be, give me a moment. I did not pre-calculate this. So maybe take this moment to also calculate this number, if you will. 72, there we go. All right, negative 72. And it looks like we're gonna have to scooch a little to the side here to finish this off. So we're left with negative 72 is equal to x minus 32. So now we're going to add 32 to both sides to isolate our x. And we get that x is equal to negative 40 degrees Fahrenheit. So by using our little trick, we found when they're numerically equal, which is going to be at negative 40 degrees, both Fahrenheit and Celsius, those values will be equal. All right, so now we're going to move on to a little bit more lectures. So if you have a set of data points and you use a different 2 points each time to create linear equations, then there's a really good chance that each equation is going to be a little different. The data itself is not perfectly linear. So you'll also probably end up missing data points when fitting a linear expression or a linear equation to data. So every time you create one of these linear equations and you match it to your data, each time you use 2 different points, those 2 points that you pick, that line will always go through those 2 points, but there's no guarantee that it will go through another set of other data points. And so when you want to create a linear equation for a set of data, you're trying to get a linear equation that is going to go through as many data points as possible, or at least best estimate. So it can be really difficult deciding which linear equation is the best. So what we calculate is what's called a residual, just to measure that error. And so the residual is, if you're looking at a graph, it's going to be the distance between your linear expression and the actual data points. And I have a picture which is a little farther down. But if we look here, this distance here is going to be the residual. This distance right here. See, we have this, which is our model, our linear model. So these are the points in our model. And then our blue points will be our data points. And so we see that there is this distance here. And this distance calculated is the residual. So we'll go into how to calculate this. Oh, it's taking a minute. Come on. There we go. So if the data point we have is supposedly x, y, but the point on the line is we're going to call x, y. It's got a little, well, it kind of looks like a little carrot on top of it, and we're just going to call that y hat, because it kind of looks like it's wearing a hat. So your data point is x, y, but your point on your line is x, y hat. Then the difference of y minus y hat measures the error in the model, also known as the residual. So that y hat value is what our linear equation gave us. But our x values are always going to be the same. The only thing that will change is going to be that y value. So one way we can determine how well a line fits the data points is to compute the sum of all the residuals. So this would be, if we're looking at our picture here, we would be finding the distance between each one of these points here. And we would be adding these distances all together. And a negative distance, this would be a negative distance, and here this would be a positive difference since it's above and then below. So we would add all of these up together. So we know that we'd be adding positives and negative values together, and maybe eventually we end up getting a value of 0. So a value of 0 doesn't necessarily mean that there's no error. It could just mean that the residuals themselves cancel each other out because some will be positive and some will be negative. So just because we got 0, that doesn't mean that there's no error. Or we could have a myriad of other issues that we have with just summing the residuals. So it's not exactly the best way, but a much better way to measure the error of the model is to compute the sum of the squares of the residuals. So what we'll do instead is we'll take these residuals and we'll square them. And when we square values that are negative, they become positive. So what we're essentially getting here is that we'll have a full positive scale of numbers. And when we add them up, we'll get a better estimate of how well the line fits the data. And so thing to understand is that a smaller sum of our sum of squares of residuals will mean that there's less error, and that means that it's a better fit. A larger sum will mean that there's more error and it is a worse fit. So we're going to go on to another example, which is going to be number 11 in your book. This is example 2. And we have here a number of years. So we have years 2007 through 2011. And then we have the number of federal credit unions. That's going to be our Y value. So we're going to treat x equals 7 as the year 2007. We're going to use this information above, and we're going to answer parts A through C. So for part A, we just want to find the residuals and the sum of the residuals. So I'm going to use a different color here. Let's just use navy blue. So our first data point, if x equals 7 is the year 2007, and we have our actual data here, then we're going to get 7 and 5,036. And then our next point is going to be 8 for the year 2008, and 4,847, 9 for the year 2009, 4,714, 10 for the year 2010, and that's going to be 4,589, and then I'm going to have to remember, I can write it. We have 11 for the year 2011, 4,447. All right, so we have our data points from our chart that we originally had. And now we want to make our models. All right, I forgot to fill in the equations that we are given. So let me write that now. This originally gives us 2 equations to use. So our first equation that's going to be y is equal to negative 143.6x plus 6,019 . Our second equation is going to be y equals negative 170.2x plus 6,250. All right. So we have our first equation and our second equation. So we're going to call our first equation, this is going to be model 1, and our second equation is going to be model 2. All right, so we have our equations here. And what we want to do is that we want to replace our x values to solve for y. So we'll use our first equation, which is going to be model 1, and we're going to replace x equals 7 into our equation for y and get our model point. And then we'll do the same thing for 7, 8, 9, 10, and 11. And then you want to find those values as well, because we remember that our x values will be the exact same. So we're just replacing these x values, and then we're finding our y values. So I invite you to take a moment and calculate these on your own. It is a little bit of calculation I have to do, but it shouldn't take too long. So feel free to pause anytime. All right, so you should have gotten for your Model 1 something along the lines of 7 and 5013.8. For your second, you should have gotten 8 and 4870.2. For your third, you've gotten 9, 4726.6. Then 10, 4,583, and 11, 4,439.4. All right, so we found these values by plugging in our different values of x into our first equation there. So now we want to find our residuals. So we know that our residual here is going to be 536 minus 5,036 minus 5,013.8. So you want to subtract those with this equation that we have here. And you can also take a moment to calculate that as well. And you should have gotten a positive 22.2. For our second residual here, corresponding to the year 2008, we should have done 4,847 minus 4,870.2. That should give us a negative 23.2. And for our year 2009, we would have done 4,714 minus 4,726.6. And that's going to give us negative 12.6. Then we are going to take 4,589 minus 4,583. And this is going to give us a positive 6. And lastly, for our year 2011, we're going to take 4,447 and subtract 4,439.4, which will give us a positive 7.6. So now, since we want to take the sum of our residuals, we are just going to add all of these terms up. So I invite you to also take a moment to do that as well. All right, so if you added all of these terms together, you should have gotten negative 0.1. So that's very close to 0. So in our opinion, if we were only taking the sum of residuals, we would think this is definitely very close. But since we know that the sum of the residuals, anything close to 0 can just mean that our residuals are actually just canceling each other out. So that is the case here. Our residuals are canceling each other out so much that we get very close to 0. But that does not mean that our line is actually that close or that accurate to our data. And now I want to do the same thing for model 2. So now we're going to be plugging in our values of x into our second equation here. This equation right here. So you want to do that for each value of x. So we have 7 through 11. And you want to calculate these to get your y hat values, which we are going to plug into our model 2 here. So once again, I invite you to take a moment and calculate these on your own. And now we can fill them in. So we have our model 2 point here. We're going to have the same x value as before. So we have 7. And if you've done this on your own, you would find that we would have had 5,058.6. For our second or year for 2008, we would have 8 and 4,888.4. Our third, which corresponds to 2009, we would have gotten 4,718.2. For our year 2010, we will have 10 and 4,548. That's it, no point, there we go. And 11 for year 2011, we're going to have 11 and 4,377.8. All right, so now we have our model 2 points here. And we're going to do the same thing as before. We're going to get our model 2 residuals using our y minus y hat 2 from our second model points. So once again, take a moment to calculate these on your own. You pause the video and calculate those. All right, so if you pause, welcome back. And we find that our residuals from taking y minus y hat 2, so we would have 5,036 minus 5,058.6, and that's going to give us negative 22.6. Then for our second point, we're going to have, which is 8, we're going to take 4,847 minus 4,888. This is going to give us negative 41.4, not 6. For our third point, 2009, we're going to take 4,714 minus 4,718.2, which is going to be negative 4.2. For our third point, which is 10, we're going to take 4,589 minus 4,548. This is going to give us a positive 41. And lastly, for our year 2011, we're going to take 4,447 and subtract 4,377.8. And this is going to give us 69.2. So if we add these up all together, you can feel free to take a moment, add them up together. Feel free to pause the video. And you should have gotten a positive 42. So we know that is definitely a ways away from 0, but like we said before, this is not the best way to accurately find out. So for part B, we need to find the sum of the squares of the residuals. So now we're going to square each one of these residuals. We're not just going to square the sum, we need to square each individual residual and then add those up. So we're not just squaring negative 0.1 and we're not just squaring 42. We need to square every single residual that we found for every corresponding x point. So for our first 1. So we're going to use model 1 now. And it's the same equation. It's y minus y hat 1 squared. So for that very first point, and I'm going to fill in these values over here just so we remember this is x equals 7, x equals 8, x equals 9, x equals 10, and x equals 11, just so we remember those. We know this very first value here was 22.2, positive 22.2, so we're going to square that. So 22.2, switched over to navy, squared, and that's going to give us 492.84. Then our second value was negative 23.2, so we're going to square negative 23.2 squared. This is going to give us 538.24. Then our third value, corresponding to x equals 9, we have negative 12.6. We're going to square negative 12.6. And that's going to give us 158.76. Then for our x equals 10, we have just a positive 6. So squaring 6, and that's just going to be 36. And then we are squaring 7.6, positive 7.6. So 7.6 squared. And that is going to be 57.76. All right, so now we have all the squares of our residuals. So now we want to add these all up and get this sum. So take a moment to add these all up. And you should have gotten 1,284.2. All right, so we have our squared residuals for our model 1. Now we want to find our square residuals for our model 2. So we're going to do the same thing as we did before. And it looks like our very first value is going to be negative 22.6. So we're going to take negative 22.6 and we're going to square it. And this is going to give us 510.76. If at any point you would like to calculate these on your own, please do not hesitate to pause the video at any time. Then for our x equals 8 point, we're going to have negative 41.4 squared. So negative 41.4 squared. This is going to give us 1,713.96. For our x equals 9, we have negative 4.2. So we're just going to have negative 4.2 squared. That is going to give us 17.64. Our corresponding x equals 10 value, which is going to be a positive 41. So 41 squared, which is 1,681. And lastly, for our x equals 11, we're going to square 69.2. 69.2 squared. And that is going to give us 4,788.64. So feel free to take a moment and add all of these together. And you should have gotten 8,712. All right, so we see that the sum of our squared residuals for model 1 is going to be 1,284.2, while our squared residuals for model 2 is going to be 8,712. So if we remember what we stated earlier, we said that a smaller sum is less error and a better fit, and a larger sum is more error and a worse fit. So for part C, it's asking us which linear equation is a better fit. So our smaller value is corresponding to model 1. So model 1 equation is a better fit. And this equation was y equals negative 143.6x plus 6,019. So that equation was the much better fit since it had a smaller sum of our squared residuals. Now we see that the sum of our residuals, this could also mean that it was a better estimate than our Model 2 residuals, but we had no way of truly knowing until we found our some of our squared residuals. All right, so we're on to our next part. We have linear regression. So the line of best fit is also known as the least squares regression line, and the computational process for finding its equation is called linear regression. And these formulas are very complicated and they require a lot of computation, but luckily graphing calculators can do it very easily. So if you have a graphing calculator, this section can be extremely useful to you for learning about linear regression lines. And this section also talks about our correlation coefficient, which is just a value that assesses the fit of the linear regression line to the scatter plot. This is often referred to as R, and R is always between -1 and 1, where 1 is a straight line with a positive slope, -1 is a straight line with a negative slope, and anything close to 0 will show a curve or a circle. So this linear regression, this is just telling us if our line of best fit is going to be accurate or not. So this is a much quicker way of kind of finding this if you have a graphing calculator and are able to do it. And then this correlation coefficient will also tell us how good of a fit was it. So if it was anywhere between -1 and 1. So like I said, if you have a graphing calculator, feel free to try this section out. I strongly encourage you to. It's a very useful tool. But since this class only requires a scientific or graphing calculator, I personally am going to opt out of this session. So questions relating to this material will not be on your homework, quiz, or test, or your final. Anything relating to Chapter 2, this part will not be included on. But if you do have a graphing calculator, once again, I strongly encourage you to go through and you take a look at it. It's a very helpful tool. All right, so that concludes our section 2.3. So if you have any questions, please don't hesitate to email me at all. If you would like to submit an anonymous question to our question form, I highly suggest that as well. So if there's anything you would like to talk to me about, either feel free to email me or put in that question form. I'll be piecing together the review for tomorrow, so please send me anything by either tonight or tomorrow morning that I can have it in on that review. All right, so I hope you all have a great rest of your day, and I will talk to you virtually soon.